Okay, it's 2:02 right now. Let's get started. So hello everyone. Welcome to Ask Seminar Series. This is John. So I will be the moderator with Kathy Medley, our communication specialist. Also joining us is our director, Prof. Ferrero. And Prof will be introducing a speaker before she gets started. And just so you know that this seminar is being recorded, and we will publish video recording on the YouTube ASIC channel. And we encourage you to ask questions after the presentation. You can do so by speaking out, or you can chat us your questions. Before the speaker gets started, we'll have our director, Prof. Ferrero, to introduce the speaker. So Prof, please go ahead.
Yes, thanks, John. And yeah, welcome. If I say your name wrong, it's Noemi Vergopolan. It's like
Almost there. Noemi, Vergopolan.
Noemi. Okay.
There you go.
All right. Sorry about that. So yeah, welcome. She's a computational hydrologist, working as I believe visiting scientist at NOAA's GFDL, just up the road from us in Princeton. She got her PhD in civil engineering at Princeton recently, or civil and environmental engineering, and it's going to be starting a new position at Rice University this summer, I believe. So she does a lot of soil moisture and land surface modeling, and we're going to learn a little bit more about that in her talk next. So welcome and thanks.
Thank you, Rolf and John, for the invitation. It's my pleasure to be here today. We'll be talking a little bit today on, as a hydrologist, a lot of the problems we care about and we focus about is how water changes in space and time, and how these changes will affect how we deal with water. Too much water, too little water, challenge linked to food security, ecosystems health. So essentially, the focus of my research is to better understand how climate change will impact water systems and thus impact the process linked to water. And one of the key variables that's connected to floods, droughts, food security, ecosystems health is soil moisture, right? Soil moisture, why is that so important? Is the variable that controls fluxes of water, energy, and carbon from the surface to the atmosphere. So it's how we interact, how lands interact with climate. It's important if you want to understand too little water, impacts of droughts, and water storage on the ground. Soil moisture is also important control for wildfires as a preconditioning to better understand vegetation load, and they call it fuel load for wildfires. Antecedent conditions on the other extreme that would lead to flash floods in flash flood intensification of flash flood peaks is also can also be controlled by soil moisture. Extreme soil moisture also plays a role on understanding landslides in the specific and sensitive thresholds that leads to soil to lose cohesion and lead to soil, movements. Soil moisture is also important to understand initialization conditions for weather and climate forecasts, particularly during drought events, to understand water demands for agriculture and crop productivity as well. And on the other extent, too much soil moisture can also be critical for understanding water logging conditions and where and how much do we need to drain tiles to improve crop fertility. Another important component of soil moisture is how it drives biogeochemical cycles. All the process links to water in wetlands, for instance. Spatial and temporal distribution of microorganisms in the soil, as well as their ecosystem services. A spatial temporal distribution of flora and fauna and animals that needs moist in the soil for their living and reproductive pathways. Epidemics, disease, as some of the mosquitoes that drive some, for instance, malaria, Aedes vexin, do need the moist soil to hatch their eggs and continue their reproductive cycle, as well as military applications, as you think of soil moisture as a preconditioning variable for military logistics. And so there's a vast, broad applications of soil moisture in our society nowadays. But one of the challenges with soil moisture is many of these applications are linked to soil moisture in a non-linear way. So effectively, if we think as this evapotranspiration, how much water evaporates from plants and from the ground and plants transpire to the atmosphere, that's and also controlling, right? Water in the soil also control photosynthesis rate. So how much CO2 is also uptake from our atmosphere. That's effectively a non-linear process, often represented by the Bodico curve, the classic curving in hydrology, which is highly non-linear. So at some point, not necessarily more soil moisture will increase evapotranspiration from the land. Another critical process, for instance, nitrification. As farmers apply fertilizers in the soil, there is an exact amount of moist that the soil needs to have, such that the plants will actually be able to uptake these fertilizers and not lixiviate them through the river to the river in riparian zones. And we can spend the whole afternoon discussing how different processes in our earth system are linked to soil moisture in this non-linear way, right? So one big question that emerges is, okay, so how do we measure soil moisture? How do we obtain soil moisture? How do we understand how this process change? One way to measure them, the most accurate way, is through gravimetric measurements. So effectively, researchers will go collect a sample of the soil in the ground, take it to the lab, scale, dry the soil, and estimate what was the water content in the soil particle, right? These are very expensive and laborious. To overcome this challenge, the community has developed proxies, which are based on electrical resistance, the electric constant, and other sensors, for instance, with neural interaction. These sensors are a little bit more scalable, but they still require ground calibration in each location. And they still are very expensive and not widely available. Although, as of right now, they represent the most accurate retrievals that we can obtain at a point in local scale. On another range of change, we have satellite observations, for instance, such as the SMAP, a soil moisture active passive mission. It's a global satellite mission that retrieves soil moisture every 2 to 3 days revisit time, but it has a coarser spatial resolution of 9 to 36 kilometers resolution, 9 being the sample product. And it's also a proxy measurement. It measures actually brightness temperature, and it relies on something called a radiative transfer model to effectively convert this brightness temperature measurement into soil moisture, right? And another way we can use to predict in soil moisture is through using earth system models. And earth system models are our best representation of the complex earth system through physical equations, right? So they are numerical models, and these models are effectively integrating different components of our earth system, including the atmosphere dynamics, ocean dynamics, cryosphere, and land, right? So effectively, when we are talking about soil moisture, we're interacting mostly with the land surface component of these models, but the nice goal of using earth system models is that they do interact with the other components. So thus we can start to evaluate and better integrate how land interacts with the atmosphere and so on. These models, however, are highly computationally expensive. State-of-the-art models is still operated at 10 kilometers of resolution, which is still a little bit of some coarse scale. But they do help us better understand the processes and how they interact with each other. So when we think about these different soil moisture data sources, one of the challenges is that soil moisture is highly variable in space and time. So if you take a domain of, for instance, 36 kilometers resolution, as illustrated here on this on this plot on the right. Even if we're lucky enough to have 3 in-situ measurements in this domain, they're very unlikely to be representative of the broad variability of soil moisture across the landscape, right? Satellite observations, as I mentioned, they are too coarse. They might have 1 point information across this entire domain. So also very good in terms of getting the overall dynamics, but hardly representing the variability that we see on the landscape. Hydrological models and earth system models can help us getting a little bit closer in terms of spatial resolution and spatial representativeness, but they're still too coarse, particularly if we're talking about processes that we need information for decisions that happen at the sub-kilometer scales. So as we think about irrigation, landslides, flooding, they're also often sub-kilometer processes. So as of right now, we have this unresolved spatial scale mismatch between the scale that we observe processes, we model them, and the scale that we effectively need the soil moisture formation to address some of these terrestrial water grand challenges, right? So what we need effectively moving forward are integrated approaches that can thus reconcile these scales. The scales we observe the process, the scales that we measure them, the scale that the process actually happens, and the scale to which we observe the impacts of changes in water variability in our earth system, and in our society. Today we live in unprecedented times, which now we have the availability, vast availability of satellite Earth observation, statistics and machine learning methods, advancements in Earth system models, and numerical schemes. I'm going to address a little bit in these talks, vast computational resources availability, as well as a vast range of satellite observations at very high resolution, as illustrated some here on the right of my slide. So big question that comes is, how can we now leverage these unique opportunities that we have today, and we didn't have perhaps 10 years ago or 5 years ago, to better understand and predict soil moisture dynamics at the local scale, and better understand these interactions with some of the terrestrial water grand challenges, right? So in this talk, I'm going to effectively introduce an approach that we developed to improve realism into these Earth system models and better represent these processes with more spatial detail. An approach to reconcile the scales between how we observe soil moisture and how can we predict them. And some analysis on investigating this hydrologic scaling of soil moisture and how we can benefit our better understanding and use of this data for water and climate challenge, right? So let's get started with the first topic, which will be on advancing realism in these models, right? As I mentioned earlier, the land surface model components of Earth system models are the components in charge of simulating and representing soil water dynamics, right? These land surface models are usually split in 3 components: energy balance, water balance, and carbon balance, right? And they simulate all this process in an interactive way. We're effectively be working with the water component to simulate soil moisture. And what these models do, they solve, for instance, Richard's equation, which is one of the classic equations to understand how water moves in the ground, is based on Darcy law. And we can effectively compute at the different layers of the soil how moist, represented as theta, would change over time as a function of, for instance, the elevation, the hydraulic conductivity of the soil, the soil water potential, and hydraulic conductivity, as well as sources and sinks that you can think as precipitation, evaporation, lateral flow, and so on. These models are solving these numerical equations usually comes in these land surface models that are often organized in 2 flavors. We like to categorize them. They can be often distributed models or lumped models, right? So in distributed models, we're going to use all the finest resolution information that we have about meteorological data, soil parameters, land cover parameters, and so on. And this is going to yield a distributed response. On lumped models, on the other hand, we assume we don't know much about what's going on within a catchment or within the sub-kilometer scales. So we just average the meteorological input data and the parameters, and thus, as a response, we have an average response of a given catchment, for instance. What happens is that fully distributed models, they're much more realistic in terms of representing what can be happening in a catchment, but are highly computationally expensive. Lumped models, on the other hand, they tend to be oversimplistic by neglecting the process that can happen within the catchment, but they're computationally cheap and very easy to scale across larger domains. So effectively, what we want to find is, can we find a spot in between, an optimal place where we can take advantage of both the realism of distributed models and the computationally cheap aspect of lumped models, right? And this is where semi-distributed models comes into play. Right. So one of the concepts that have been developed over the past years, it's not a new concept, is the idea of hydrological similarity. And this concept says that areas with similar climate and landscape characteristics will yield a similar hydrological response. So back in the days, what researchers used to do is to overlay maps of characteristics of the landscape, soils, topography, climate, and hand delineate these areas of similarity to then create the computational mesh for these semi-distributed models. Today, we can do this in a much more elegant way, for instance, using machine learning, where we can cluster areas of similar hydrological characteristics into what we call a hydrological response unit. So for this example catchment here, the Walnut Gulch, if we use, let's say, 3 clusters, we could represent the variability of this catchment, or where are the areas that are more similar than others, effectively representing riparian zones, lower river basin, lower part of the basin, and upper part of a given basin. Of course, in reality, we don't use 3 clusters, right, to represent this variability. We would use 50 to 500 clusters to represent this heterogeneity in the uniqueness of a catchment, of the characteristics of a catchment, right? But this, in comparison to a fully distributed model, which would take, let's say, 1 million 30 meters grid cells, represent like a substantial order of magnitude reduction in terms of how can we still represent it with a lot of realism with a reduced computational cost using this semi-distributed approach. But so the beauty of this approach comes when we effectively can reconcile this idea of clustering high-resolution proxies of land variability and organize it in a hierarchical way to identify, for instance, hill slopes of catchments and sub-discretize them into tiles, or effectively clusters. What we do then is to then connect these tiles and clusters in a hydrologically coherent way to identify what is our computational mesh of these numerical models, right? And the beauty comes when we can actually couple this mesh generator with a physically resolving land surface model. So in this way, we can reduce the computational cost of simulating fully distributed processes by like 500 times, achieving an effective 30 to 100 meters resolution, and still keep it physically consistent with our traditional land surface and physical models. What I would like to show you now is an example of coupling this approach over the United States to demonstrate its potential and its scalability. So we collect data, like this big environmental data sets at 30 meters resolution in the US. We apply the hydroblocks approach to identify these hydrological response units and clusters, and we couple to the Noemi land surface model. We fitted this model with the highest resolution data sets that we could find across the US in terms of elevation, soil types, land cover, and as well as meteorological data. And we evaluated the 30-meter soil moisture simulations that we can obtain by using this approach. So just to give you a sense of scale here, the United States has 7.7 million square kilometers. To perform the simulation, we can use 5 million tiles instead of 8 billion 30 meters grid cell that we would use if we were to perform a fully distributed simulation, right? This simulation was in a 3 hour 30 meters effective resolution from 2010 to 2019, using 300 computing units in the Princeton University HPC facility, right? And then I would like to show you now an illustration of this simulation of soil moisture across the US. So as you can see, this approach enables us to represent with a lot of realism a lot of the interactions between soil moisture and the landscape. For instance, we can observe the imprint of big rainfall events coming through all the way from the west to the east of the US. We can observe how soil moisture interacts with the subsurface, replenishing water in the soils in the riparian zone shortly after the rain events. We can observe the different soil moisture memory across the US, particularly if you look into over the west of the US, which is mostly dry and sandy soils, versus the US Corn Belt, which actually struggle with challenges with such as waterlogging conditions when the soils are often difficult to drain. You can also observe interactions with big tropical storms that move all the way from the south of the US to the northeast, and how these storms also interact and affect soil moisture dynamics and subsequently all the processes linked to that. Can also, we can also look into the same soil moisture simulations, now looking at a very local scale. So we can zoom in here, for instance, over the lower Mississippi river basin. By using such a big environmental data approach, we can capture with a lot of realism the interactions of soil moisture, for instance, as shown here with the sand dunes, interactions with the reservoirs, right? And how reservoirs change the soil water dynamics upstream and downstream, right? Interactions with your big urban centers and how they modulate and change soil water dynamics in the landscapes, as well as capture some human interventions, such as if you can observe here in the center, rice paddy irrigation. So some human activities that are often challenged to represent with these models can be captured with this approach. Give you another example here. This is Sacramento Bay Area, where you can compare with a visible imagery. We can represent well the dynamics with wetlands. So how wetlands interact with upperland. Again, here representing big urban zones and how they change soil moisture dynamics. Some of the infrastructure, water infrastructure features can also be represented using this approach. Interactions with topography and aspect, and how that change, how different radiation levels will change soil dynamics in different locations. But these are models, right? This is a highly realistic computational mesh applied to a physically resolving model. They're still limited to our capabilities and to the uncertainties the input data have, and also as importantly, the processes that we're actually representing in this model. So there are still some things that we don't do really well. And you'll be able to see in this area here, in the northwest of the plot, is that we can not just simply by using just models, we cannot capture the imprint, for instance, of local scale irrigation, right? Individual agriculture fields that have more dynamic variability than full-time irrigated fields such as paddy irrigation. So there's still some challenges on these models on representing processes that we don't have effectively physically resolved equations that can ensure that them happening at the right and certain time, right? So we have the model capabilities that we can improve realism in estimating soil moisture. The question that comes is, how can we now take advantage of satellite and in-situ observations to effectively bridge this gap the models cannot always reconcile, right? And one way forward is to data fusion and data simulation, right? So one of the next things we did is to develop this approach that we call as map hydroblocks, which is effectively a way to combine now this soil moisture estimations from land surface models with satellite remote sensing and in-situ observations. So what we did here was to then take these simulations of soil moisture at the effective 30 meters resolution and combine them with this map, map observed brightness temperatures. So to do this, we first coupled the reversed tau omega radiative transfer model that SMAP uses to estimate what would be the brightness temperature that the satellite would observe for a given soil moisture value that my model is simulating, right? So given this model simulated brightness temperature and the satellite effectively observed brightness temperature, we can combine them. One way to combine them, for instance, is through spatial Bayesian merging approaches. However, we know that there are errors in the models and processes that are not being represented, but there are also uncertainties on satellite observations, right? They could be due to interference, dense vegetation, specific types of soils, calibration, ongoing calibration, and so on. So to learn what are those uncertainties and what are the physical characteristics of the different soil types, hydroclimate, vegetation, conditions that are driving these errors and differences between models and satellite, what we do effectively is to train a machine learning model with most of the available in-situ observations that we have in the US to learn these uncertainties and errors and use this learned information to effectively merge and obtain the optimal state of brightness temperature between model and satellite observed fields. After we merge the brightness temperature, we can feed them back into the reverse, the actual tau omega radiative transfer model to then obtain a data fused 30 meter soil moisture estimate at 30 meters resolution, right? The beauty of this, the use of reverse and merging with radiative transfer model is not that novel, but the beauty of this approach is that both the modeling and the data fusion is performed at this cluster space that reduces the matrices operations that one needs to do for data fusion, data simulation by 300 to 400 times. And that's what's effectively make this approach feasible and scalable across continental domains. What we have done next is to then actually apply this approach across the continental United States and develop what is up to now the first 30 meter space satellites-based surface soil moisture for the US. I won't have the time to go extensively into the validation of this data set, but I want to cover you may be able to find more details in our paper, but I want to cover very quickly assessment we did in terms of its spatial representativeness. So we compare the model, just our model simulations, just showing in red, with the SMAP L3 and L4 products from NASA in terms of its spatial correlation using in-situ observations available for the US. And what we can see here is that there is a consistent higher spatial correlation just from a high resolution model per se, without any observations of soil moisture driving these results. But when we fuse effectively the model simulation with SMAP observed brightness temperature, we can observe a consistent higher spatial correlation for the continental United States. We have seen similar patterns across some of the dense networks over the US, such as the New York Mesonet and the Oklahoma Mesonet, with this data fused products showing consistently improved spatial detail, right? So as a summary, this data set is available, is open access now. It was developed initially as a proof of concept. So it's as of right now only available from 2015 to 2019. It had a 2 to 3 days revisit time according to SMAP retrievals. We've been working on this on some drought to assess drought conditions and drought impacts For instance, some collaborators in USDA have been attempting to use this to better understand how droughts and to look into soil moisture can affect like irrigation, water demands. And collaborators in Illinois University have been using this data to better understand how soil moisture is affecting waterlogging conditions through also data simulation approach. Some collaborators in the southeast of the US has been using the soil moisture data to better understand the spatial distribution of invasive species in the area. So there is lots of, given that soil moisture is linked to so many of our groundwater challenges, there is lots of applications going on and possible for the future as well. So now that I'm moving to Rice University, one of the short-term objectives is to expand this data set for global coverage into current date. We plan to update some of the data fusion approaches using now temporally varying deep learning models, as well as integrating other sensors that maybe we'll be able to now capture with more fine scale detail local scale irrigation in wildfires using, for instance, thermal, infrared, and SAR sensors that weren't using this approach, but the research has been built in the framework that will enable us to also ingest that as we move forward. With this data set, we're now able to answer for the first time some of the basic questions in hydrology that we couldn't even think about answering before, just because we didn't have the data available to answer these questions, which is, first of all, how soil moisture vary at the local scales, how this variability persists across scale. We will actually need 30 meters resolution data to understand soil water dynamics in terrestrial water challenges that we are facing, right? So to first address this question as a first attempt at looking the data, one of the things that we computed was the spatial standard deviation to identify what are the places in the US where soil moisture varies the most in space. So by computing the spatial standard deviation at each 10 kilometers box over the US, we can see here is that most of the variability is observed on the southeast of the US, southeast coast, and near the US Great Lakes, right? Which is a bit counterintuitive if we think many of us expect most of the variability to be linked to the high elevation locations over the west. So what we did next was to effectively compare to a principal component analysis what are the physical characteristics at each of these locations that drive some places to have more variability than others. And what we found here is that, as expected, precipitation is one of the major drivers of variability in soil moisture. So wet soils are likely more variable than drier soils, but also variability in soil properties per se. So if I'm not showing the slides here for sake of time, but if we normalize this soil moisture standard deviation by its mean value, by the precipitation, disentangling the precipitation, we see that this variation in soil properties are actually what drives the most soil moisture variability over land. One question that comes next is like, okay, some areas are very variable and there's a lot of detail on this fine scale soil moisture dynamics, but how much of this local scale variability matters? Is much of this noise or not? Can we capture this variability using, for instance, coarse scale products or coarse scale data? To answer this question, we perform synthetic spatial scaling analysis, which relies on taking this 30 meters data and coursing to 100, 240, 450, 1 kilometer resolution, and then compute to what we call here information loss, which is effectively a relative change in the soil moisture spatial standard deviation at each of these locations. So what we found out is that in some locations, for instance, first row here, location 1, we only see a 21% reduction in the spatial standard deviation of this domain, which means that most of the features captured at the fine scale are retained at the coarser 1 kilometer resolution here, right? But in other locations, such as location 7, what we see is that when we coarse the data from 30 meters all the way to 1 kilometer, we lose up to 74% of the variability, which means that all the riparian zones, the perennial rivers, vanish at this scale. So we are effectively neglecting their existence and not accounting for them simply by a scaling behavior issue here. What we did next is to perform this computing of the information loss across the entire United States. And what we saw is that there's a large loss of variability, and most of the variability that we see at the 30-meter scale does not persist at all. When we move even from 30 meters to 1 kilometer scale, much less will be to the 10, 25, or 50 kilometer scales that are the scales that we're actually using in our climate prediction models. Up to half of the US shows at least 48% of information loss from 30 meters to 1 kilometer scale, right? And what we do with this information, well, effectively we can overlap these maps. So for instance, overlap where soil moisture is mostly variable in space, where we have the highest information loss if we rely on coarser data, and map, as shown here in this third map on the right in dark red, the areas where we have high soil moisture variability and high information loss at the coarse scales, but also low soil moisture variability and high information loss, because those areas are also important. And mapping those areas might help us improve design of sensors of networks. So these are effectively the areas where we need more sensors to better capture this variability. These are effectively the areas where we need higher resolution spatial and temporal data, because many of these processes that vary non-linearly of soil moisture might be underestimated or undertaken into account if we're using data that are not representing this process that happens at the sub-kilometer scales. I would like to start to wrap up this presentation by giving some examples of some of the projects we've been working on looking to how soil moisture, defined scales, interact with some of these processes in groundwater challenge that we addressed today. One of them is drought, right? So today we have the US Drought Monitor, which is excellent, state-of-the-art globally. But these rely on historical soil moisture simulations that are often also driven, I think, 25 kilometers resolution, so very coarse scale and very likely not representing this local scale process and dynamics happening at the sub-kilometer scale. It's no surprise that if we cross the drought intensity maps reported by the US Drought Monitor with stakeholder reported drought intensities, we see a huge mismatch between what we are actually predicting and monitoring in terms of drought and what people are actually facing the ground, right? We use this high resolution soil moisture data to perform another synthetic scaling approach to investigate to what extent actually just by having high soil moisture data can we improve intensity detection of droughts in terms of the area and its intensity. So we computed using the soil moisture percentile method the intensity of drought at 4 different locations. This was study done in Africa, actually. One at the local scale, district scale, province scale, national scale, right? We use a 250 meters soil moisture data as a benchmark, and then we coarsen the soil moisture data to 5 kilometers, 25 and 50 kilometers resolution. And then we recompute what would be the soil moisture percentile and use it as a threshold. Anything above the driest, we only take into account here the 20% the driest events on the record, on the historical record for each of these resolutions. So if we look at let's say one resolution here, 25 kilometers resolution, and we zoom in, is what we see is that simply by using soil moisture data at a coarser resolution, we underestimate drought area by 37% and intensity by 21%. Right, the similar levels for district scale and province scale. At national scales, even coarse data is doing a pretty good job in terms of capturing in terms of drought intensity, but overestimating a little bit the drought area that is happening. So the big takeaway here is that, okay, we care a lot about soil hydrology and processes happening at the sub-kilometer scales, but a lot of the decisions that we take today, think about large-scale hydrological models, hydrological monitoring system, future climate projections, they all rely on models in information data on soil moisture that's still operating at 25 to 50 kilometer scales. They're likely underestimate both the intensity and the effectively location where droughts are happening. And this can have important implications if you think as like warning, disaster mitigation, as well as insurance payouts and so on. Right. What we have done next is to use also this soil moisture information in developing countries, couple them with machine learning models to reconstruct historical crop yields in developing countries. So that can also help improve information for places that are often unmeasured. So they don't very hardly have ground in situ soil moisture observations. But having a sense of first order data sets to help them can help us also improve decision making. We have done another study trying to understand how farmers are biased when they take decisions on when to plant, on when to irrigate, when to apply fertilizer based on what they think they know of soils, of moisture in the soil. So we can start to use these methods and data sets to help better understand droughts, their impacts on crops, how decisions are made all the way from the local scale to more regional, national and regional scale as well. Some of the research that we're doing now in GFDL, it also interacts with soil moisture, but it's mostly on the line of reconciling scales. We have coupled these hydroblocks framework with NOAA GFDL Earth system models, and we are now doing a simulation of vegetation biomass, taking into account Jedi canopy height measurements and Moody's LAI, to then compute what would be biomass distribution over leaves, sapwoods, and roots, and assimilate those into Earth system models. And this is mainly because Earth system models are slow and computationally expensive to run because they need to be spun up for a very long time. Vegetation models often need 300 years of model spin up. However, if we can use remote sensing observations to then initialize vegetation conditions into these models, we can have a great improvement in terms of computational cost, but also realism and accuracy into them. So we developed this method for simulating vegetation biomass. I show here an example over the Appalachian Mountains where we can represent to some extent the variability of vegetation, living vegetation biomass using 40 clusters instead of 1.2 million 90 meters grid cell over this domain. We have extended this analysis also over the North America, and we're working to now implementing this into a global setting. So effectively using this machine learning, big data, and data fusion approach to reconcile the skills that we actually observe the process and the skills that we can actually make good use of them into computationally expensive models. The next step would be now to combine all of them together, combining novel mesh generation approaches with detailed Earth system models, assimilation of vegetation biomass, and assimilation of soil moisture states consistently in the GFDL land surface model. And the long-term goal here is to then use these data simulation products as initialization conditions for the weather and climate forecast. Here at GFDL, we work more on the research development, but ideally, our goal is that this research will found the foundation, the ground, for a new land data simulation approach that they'll be able to support the efforts from the United States unified weather forecast systems in the next few days. And I want to conclude with this slide that I brought up earlier in this talk, is that there is still many other processes that varies non-linearly with soil moisture, and then have a complex behavior that we haven't still explored. So there'll be plenty of research opportunities moving forward to better understand how the spatial variability in soil moisture will also impact hydroclimate, crop productivity, landslides, droughts, floods, species distributions, and so on. So I want to conclude this talk by actually leaving an invitation for the audience who has working or experts on these specific topics, if they would like to better explore some of these spatial temporal linearities, that would be something I would be excited to collaborate. And with that, I conclude the talk of today, and highlighting again, right, this need of reconciling the scales, how we observe data, how we model this process, and how can we effectively use these tools to improve decision-making and our access of hydrological information to better improve and address some of this surface water grand challenge. And with that, I thank you for the invitation.
Thank you. So we have a lot of questions already. So if anybody has any questions, I'm going to go through the ones that we have. I'm going to say everybody's name and then just cue you to speak aloud. If you don't have a microphone, please just indicate so in the chat. There's just a lot, so it's definitely better to everybody can just ask it aloud. And then once we're at the end, I'll let everyone know so they can open for more questions. But we have a lot of questions to go through. So Alex Hernandez asked their first question.
I think I open here the Alex, are you gonna talk? I open the chat. I can also answer for here. So how you prefer, Alex? So Alex asked if I have plans to extend the time series to present. Yes, it's a high priority on my to-do list. It's just I've been in the middle of a transition between institutions, so I stay on the watch for the next year or so. We might have a new version with extended time series as well.
Okay, we want to move on to our shot 3 at Tulane. I would assume I don't know, they're going to be able to unmute themselves.
Do you want me to ask the question?
Oh, yes, please.
Oh, hi, Noemi. Thank you for sharing about this new product. So I have a question, like, did you perform any calibration of this developing product? And like, if at what stage did like calibration?
So great question. There is no calibration involved. In terms of land surface model, no calibration at all, no MP pretty much out of the box. And that's because I wanted to keep the model as unbiased as possible, such that I can trust it to some extent when I transfer to other locations where we don't have observations. So the land model is not calibrated in that sense. The only moment where I use in-situ observations of soil moisture is to then, when I'm gonna do the data fusion, to effectively learn the biases between the satellite observations, the models, and in the ground observations. So that's the only moment. So it's not a calibration, but I do use in-situ observations when I'm gonna inform the data fusion approach. But yeah, the model per se is not calibrated.
And how much time it take like to run for, let's say, a basin of Mississippi size? Like if someone need to run it.
It doesn't, because it uses these hydrologic response units, the clusters, it's not too computationally expensive. And that's one of the main advantages of this approach, is to reduce computational cost. I would say that will depend probably a few hours for a day of run, like 2 to 3 hours for a model simulation, 1 day model simulation for the entire basin, which is big. So to give you a sense, this whole 10 years of model of this simulation, 10 years, 3 hourly for the entire US took me a week with 300 cores. So maybe you can make the math from there on the area of Mississippi, because I cannot recall the area here top of my head. But it is computationally intensive, but not for the state-of-the-art HPC systems that we have today.
Do you want me to ask, like, I had one more question in the
Sure.
Okay. Have you compared with any on-site deeper soil moisture information, how your model perform, how this
I have not. Great question. When we did this study, we only looking into surface values, because it was the first attempt, the first ever thing similar to that. So we just kind of try to demonstrate its scalability. But certainly for the next version, I want to also include the propagate the assimilation of surface SMAP values to the root zone. So that's on the plans for the next version, and I'll certainly evaluate how well it does. It does on the deeper layers.
But like the one like caveat can be that like satellite-based moisture may not able to sense deeper. So that may be one of the challenges. So I will like
absolutely. Absolutely. So what the community has done is to develop exponential scaling relationships. So if we have some knowledge of what's the soil moisture dynamics of the surface layer, and we know the soil moisture hydraulic conductivity decays using a scaling relationship, there is pretty well-published literature on how to propagate these changes from the surface layer to the deep layer. They might not be super accurate, but there are ways to at least attempt to address this challenge.
Okay, yeah, thank you.
So our next question is from Owner Gungar. I apologize if I said that incorrectly.
Hello. Thank you for the presentation. In the literature, there is a big effort to estimate irrigational water use. Does SMAP hydroblock improve the detection of soil moisture for the irrigational purposes?
Yes. So, well, there is a challenge here. SMAP is, of course, footprint, 9 kilometers. So to the extent that SMAP can see the irrigation imprint, we can capture them. So what we've shown in the 2021 SMAP hydroblocks paper is that this data fusion, we can effectively map where in the US was the added value of SMAP. And what we've seen is that mostly the heavily irrigated agriculture areas are the ones that SMAP adds the most value. So we can effectively cross the highly irrigated locations with where our data simulation benefited the most. And this is in line with other studies in the US that have accessed capabilities of SMAP to detect irrigation. So to answer your question more clearly, to the extent that's large-scale irrigation, yes, we can capture that. However, like the specific fields, if you take one little field, non-irrigated and one irrigated, we're not going to be able to see that. And that's mostly because of the physical models often don't account for that. And the footprint of SMAP is too coarse. So in the next version, as I mentioned, we're going to move into assimilating also thermal and SAR data, such that we can take into account these local scale variabilities that are not accounted for in SMAP. Then I think I will be able to make a better statement whether we can detect 30 meters field scale irrigation using this approach.
Thank you.
Thank you. So Augusto, I apologize. You know who I'm talking to, Augusto.
Hi, Noemi.
Hello.
No, I was just wondering, when you showed the maps with the reservoirs, how do you account for surface water dynamics in the model? And another question that I have is, you mentioned that the model doesn't currently represent irrigation. What are the plans for that?
Okay, so when the first maps you saw was with a previous version that we have from the hydroblocks model, which did not have surface routing on that. So where you see it's where you saw a lake, it's a fake lake. It's pretty much a flooded land. It's soils that are effectively saturated. So that's why they are represented there with a value, but they're effectively soil in there. We kind of developed in parallel the surface routing scheme with the Hydroblocks version 2, which then has the two-way coupling river network and land. And we're going to use this version to the next version. We're going to use this model version to the next version of SMAP Hydroblocks. So that will be taken into account in the next version, but it's not in here. And as of right now, we don't have we don't have reservoir dynamics represented in this model, but that's certainly something that we want to add moving forward, because I think it's critical if you want to understand like water use and water location using these modeling tools. And you asked a second question, which is?
What are the plans for representing irrigation in the model? The impact
Irrigation.
of
So what I want to do is to assimilate thermal data, like EcoStrat, Landsat, and NISAR data from SAR data to be able to effectively capture the local scale spatial variability, dynamics changing soil moisture. So that's what we have in mind. Eventually, we might include the irrigation module into the physical model of Noemi, but that's not as in the short-term plans as of reconcile, like assimilating the other data sets before. But that's a great question.
Thank you.
Thank you. So now we're at Minking. Minking, do you want to ask your question? Oh, it looks like they have left actually. So I'm just going to go ahead and read their question out loud. What is the soil depth considered for the soil moisture in your models?
So the Noemi traditional model is 2 meters depth, the soil column, and I think that has like 3 layers. We changed that to run the simulation to a 10 meters soil depth, and it has 20 layers. It starts all the way from 5 centimeters, 5, 10, and progressively increasing the thickness of the soil layer up to 20 layers of 10 meters depth maximum.
Thank you. Also, we have Twistano. Let's see, is he still here? Oh yeah, do you want to ask your question?
Hi, Naomi, thank you for presentation. I would like to ask, this is very nice and very detailed. I just wonder about the coastal region. Did you consider about the ocean effects?
Great question as well. No, we do not have coastal regions into this. We don't have ocean interactions with this approach. We do have some. We're starting to develop the baby steps on our surface routing model, and I think it would be nice to add in the future ocean interactions as well. With the land for better representing coastal regions, but as of right now we don't have it. But that's a nice midterm goal for the next few years. So definitely something that we are interested, but we still don't have it included.
Okay, thank you.
Okay, so now we have Bailing Lee. Bailing, do you want to ask him?
Yeah. Hi, Naomi. Thanks. Great presentation. I'm not familiar with hydroblocks. I thought it is a land surface model on its own. You also mentioned that it solves a one-dimensional recharge equation. So then I'm not clear, why do you need to couple NoMP with hydroblocks?
Okay, great question as well. And I think in the early days of hydroblocks of this approach, we used to call it hydroblocks land surface model. Okay, it's not. We over the past few years or few months, I don't know, we are reframing to call it like that, and I'll explain you why. Because effectively, all the core physics of hydroblocks since day one have always been OMP. So we decided to call it, instead of a modeling framework, hydroblocks modeling framework instead of hydroblocks land surface model. So they are the same thing. They're effectively the same thing. But the difference is that the hydroblocks modeling framework, I like to see it as a mesh generator that can be coupled to any land surface scheme. That be OMP, that be GFDL land model, that be, I don't know, any other land model existing, it can be coupled to, right? So effectively, when it's easy to come and say, oh, I coupled this modeling, this mesh generator to a model and give it another name, but we decided to keep it separate and say this is hydroblocks with OMP or this is hydroblocks with GFDL model, such that we can still give the credits to the actual model developments for the physics behind this model, which is the actual in-car team behind OMP. So that's one of the reasons. In how the couple is done is this is also another reason why we decide to call it we rename it from a land surface model to a modeling framework, because effectively can be coupled to any model. So I like to think as the mesh. Nate Cheney thinks in a little bit different way about that. He's like, it's more than the mesh, but I like to think as a mesh because it's just much easier to convey that to any modeler in any field, being hydrology or not. I don't know if that answers your question.
Yes. Yes. Thank you.
Thank you.
Okay, I have one more question in my queue, and that's from Johnny Artega. Johnny, are you here?
Yes. Hi,
go ahead.
Noemi. Thank you so much. I have a couple of questions related to snow at the north latitudes. So how you model perform when you use NDVI that is complicated in that time, in the winter mainly.
So, okay, the model behaves the same way the standards of OMP behaves for snow. So unfortunately, snow, I don't think it's beautiful. But what happens is that the soil freezes and stay constant or saturated, stay saturated and constant until temperature reaches a threshold in terms of soil moisture. So although OMP does simulate snow dynamics, the soil, when the model says, oh, there is snow over land now, soil moisture saturates and freezes. And you can actually see that imprint on just the model simulations per se, just like right now over near the Great Lakes, you can see just like kind of saturated soil moisture staying there during the winter time. So that's a deficiency clearly, because not necessarily the soil moisture saturates when the soil freezes, right? And that's also remain constant, which is a challenge during the winter time. Now, what concerns the merging with SMAP, SMAP does not retrieve bright soil moisture over frozen soils, so we cannot do any data fusion or assimilation during frozen snow periods. So what you're gonna see if you download the data, what you're gonna see is that over the higher latitudes and over the winter months, we do have a gap in there. Unfortunately, this is a limitation, but it is what we have for now, and it's just really hard to estimate soil moisture under frozen soils. And do you have another question, I think?
Thank you.
Or,
no, the last one is
the NDVI, right? It was something on NDVI.
yeah, yeah. But
so go ahead.
no, I just curious more like what kind of daily precipitation pro do you use for the model?
So I used the downscaled MLDAS2 using radar data over the US. So this was for this one was a data set put together by me and Pam on Scripps, University of San Diego Scripps lab. So effectively, he downscaled all the MLDAS product with radar in temperature labs data sets. I can, if you want to interest, I can put you in contact with him to get the access with the data.
Thank you so much.
That's of interest. You're welcome.
Thank you. Okay, we've gotten one more question. So thank you everybody for your patience. I know it's taken us a while to get through this list. So last one is Efrain Duarte. Maybe they don't have a microphone. I'll go ahead and read it out loud. They said, thank you, Noemi, for your presentation. Very good. Currently at ARS USDA, we are working on monitoring soil moisture in restored areas in the Western US, and your research is very interesting for our objectives. We hope to contact you in the future. We will be happy to have your collaboration. My bad. My reading comprehension skills are bad. There's no question in there, but
Awesome. I mean, I'm really happy and looking forward to collaborate with everyone on this. There is so much research that can be done, like just within the nonlinear interactions of soil moisture, but also interactions with like rivers, ocean, and so literally a full plate ahead for researchers, and I just appreciate learning more from those who have expertise on these specific topics. So really looking forward. Please just send me an email, reach out, and we can start some more discussions and conversations. So it's a good question, ending question comment.
Do we have any other questions or comments just while we're waiting? Oh, Alex Hernandez asked what email should we use to contact you, but I think you just took down your slide with your email.
Yeah, I can write it down here again. You can use my new email because the current ones are going to. There you go. I'm gonna be retired soon. So.
Okay, well, thank you. Thank our speaker for such a wonderful presentation. Thank you everybody for being such an active Q&A session. That's always wonderful. So have a wonderful afternoon, everybody. Our seminar series is going to continue next week, same time, same place. Thank you, everybody.
Thank you, Amy. Great talk.
Thank you for inviting me. It was great. I really enjoyed, and yeah, I many questions, which I love it.
Oh my gosh, yeah, I also love many questions. It's so wonderful when there are so many. And if I get any more, I'll send them your way. I have your email.
Yes, or my contact or anything like that. Just reach out. Really exciting. Well, thank you again for the invitation, and have a great afternoon, everyone.
You too. Bye-bye.
Yeah.